All right. Well, that is all I have as far as what we kind of need to cover for today's webinar. And so without further ado, we will go ahead and move straight into our first presentation from Alan Haynes, which is our hydrologist in charge from the California-Nevada River Forecast Center. Alan.
All right, good morning. Let's see, make sure I get this up here. Everything look okay?
Yep, looks good.
All right. Well, we've had quite a year this last year at the California-Nevada River Forecast Center, as I'm sure all of you have with the whole pandemic especially, but we also, we've been under like a 3-year charge to kind of move all of our hardware and software systems to more of a baseline configuration so that we have central support, so that we're not strung out relying on computer programs or scripts that were written by somebody that's been retired for 5 years. Those kind of situations are not ideal. So there's some trade-offs with moving toward some of these baseline configurations that we've had to make, and some of them actually show up in some of the recalibration work that we've done that I'll talk about this past summer. But we also had, at the end of last year, the end of 2019, our development and operations hydrologist, long-term since the 2000s, Art Henkel retired. And so we were vacant until the summer, and when we were able to hire Pete Fickencher, who was our service coordination hydrologist. In my previous position, Pete was in that position. So now the service coordination hydrologist position is vacant. We have one other hydrologist position that is also vacant. It's not clear that when we're going to be able to hire or how many we'll be able to hire, but that's our current situation for staffing. Also, the pandemic, in adjusting to that, we really minimized our profile in the office, excuse me, with really minimal staffing, and we were able to accomplish a lot of our work remotely, surprisingly. One of the things we gave up for the summer, because summers are dry, and it was a way to minimize contact with other folks, is we basically took the DWR forecasters out of the mix. So we're in the process now of figuring out how to bring people back into the office, with a 25% capacity, that sort of thing. We'll have some mix of in the office and telework probably throughout the winter, but we got a plan for how we'll staff up for flood events and so forth. So let's go ahead and dive into some of the work that we've done this past summer. So the development, summertime is when we push hard on a lot of development efforts when the weather's dry, after the snow's melted. We usually have a little more time, although it's also when people take vacations. So it's kind of, you don't ever make as much progress as quickly as you want, but we do make incremental progress throughout the year too, especially during dry periods, which we had a lot of last year. So one of the big things we've done is we moved to new forcings for our calibrations. We have to calibrate our hydrologic models with data sets, observed data from the past, and we basically moved from a sparse but high quality station-based data set. This was the cooperative stations. They've been around since the 1950s. The sites are stable. They've been reporting for a long time. They're high quality controlled. There's an observer there physically able to see what's going on with the station. But we're moving to a more gridded data set that has a lot more stations in it. And this is a project, it's called the Analysis of Record for Calibration. It's a project that I've seen the Weather Service and others interested in taking on for a couple of decades. And they finally got this data set together. And we kind of plowed through that this past summer to see how we could use it in our calibrations. We've got our changes in calibration are also going to impact the ensemble traces that we put out. So we've had historically we've put out about 60 traces, 60 years that we've used. That's going to cut down. I'll talk more about that with this new calibration set. And then the underlying forcing for our hydrologic ensemble forecast system is this frozen version of the global ensemble forecast system, basically the operational model, hemispheric operational model of the Weather Service. It's an old version. It's the physics, everything are frozen so that we can use it for this HEFS. That actually we're upgrading to a new version of that model that'll force the precipitation and temperatures for the hydro model. I'll talk about that, and then work that we're doing in support of verification. So we haven't had a real good system for being able to go back and look at how our forecasts have performed. And so we've been in the effort of creating the database structures needed, populating the database with data, and then creating interactive tools that we can utilize that data for verification purposes. So with their forcings, this table here kind of shows what the different variables, precipitation, temperature, freezing level, those are the drivers for our hydrology. What we've used historically in the middle, the legacy data sources, and then what we're going to be using going forward on the right column with the new data sources. So for precipitation, it was the co-op stations that I talked about, and also SNOWTEL network that measures snow, water equivalent, and melt and precipitation with those. And then we're basically switching to go back here and get rid of that. Basically, we're using our operational mean of aerial precipitation that we quality controlled and stored. We've been collecting that data for some time. So from 2004 to 2019, that's going to be the data set that we use, plus our legacy values for the 1980 to 2004 period. We didn't have the paradigm that we've had since about 2000 for dealing with operational data, but so these data sets have a little different characteristics that we have to deal with. For temperature, it was the co-op stations is what we used historically for that. And this is where we're able to really utilize this new analysis of record for calibration gridded data set. But its period of record is 1980 to 2019. So it affects, it has an effect on our hydrologic ensemble forecast system. So the HEFS ensemble forecasts. That'll impact that. And then freezing level is interesting. That we've just kind of derived from mean aerial temperature time series historically. To come up with that, you can lapse the temperature up and down elevation to figure out your mean aerial temperatures for your basins. We've got an interesting new data source that is a reanalysis from the European model, pretty skillful atmospheric model. That they've made available to us from 1980 to 2019, and that's we get the freezing level from that model. Okay, sensitive here on the forwarding. All right, so we have these different data sets, different periods of record. They have different characteristics, different biases, excuse me. I don't know why I'm so, my voice is hard to keep steady here, but so you have different gauge networks. We've had different versions of PRISM, the climatology that helps us spatially translate point or gauge data to spatially distributed data. That data set has changed, and so that affects how you distribute your precipitation, what that looks like. And then we've also got new tools for estimating precipitation that we have to account for. So in the calibration, we did from 2013 to 2019 was one period. Then we checked for the biases in the 2004 to 2013 period and adjusted the precipitation record as needed for that. And then also the other period of record was this 1979 to 2004 with different characteristics, and that also needed to have precipitation adjusted to remove biases for that. And then I guess the 2006 event in the Truckee Basin, it was a big flood event up there. That event had to be edited pretty heavily. So this is an illustration of what what you can expect to see. Mostly what's on the right side that lists those years. Those are the years that driving HEFS for climatology beyond 15 days. That's the time series of temperature and precipitation for each of those years is basically used to force the hydrologic model based on its current states. So the current snowpack and soil moisture and all that, using the weather from the past superimposed on that to drive the hydrology, and you get historically we use the 1950 to 2017, so 50 plus ensemble members, almost 60 ensemble members there. In their new calibration, it's going to be 40 members that we're going to see. So you'll only have from 1980 to 2019. And this is a trade-off we had to make to move to this new methodology that is, it's going to have some advantages, but the value of those previous years before 1980, you have to weigh against, what data was available. It looked very different than the data set we have now. So the loss of those years, may not be that noticeable in our forecasts. We don't expect to see a lot of difference in the in the performance of the ensemble forecasts anyway. This, I mentioned, we're moving from this underlying forcing for the ensemble forecast system, this GEFS version 10, we're going to GEFS version 12. That is the characteristics of this of the ensemble forecasts with the new forcing have to be looked at, and the Office of Weather Prediction has been helping with us. They're looking at this at a national scale too. So far, not really all that encouraging as to for improvements. What they've been able to discern so far is, well, it doesn't degrade things. so at least there's that. But there's some potential that it might improve things, but I wouldn't expect too much out of this. But it's just you gotta move on to the new modeling system that's supported, by the computer architecture back, our supercomputer center, all that. They're anxious to sunset the old one and move on to this new one, and that's just how progress. You got to move on. So that's what we're doing. The work getting that ready for operational use is still ongoing. It's being finished up here the end of the summer and early fall, and then we expect to have this new version driving the ensembles late this fall after we do some more evaluation. So operational by probably December this year, and then this our national center for that runs the supercomputers that run the GEFS. They want to cease production no later than January of 2021. Then this period of record is going to be from 1990 to 2019, but it'll include the flood events of February 1986. We wanted to get that in there too, so that one is added to the period of record just to get one more flood event in there. That wasn't too long ago previously. The advantages of the GEFS version 12, it's a higher resolution model. It's got better physics and data assimilation. So ideally, it should perform better, but we may not see a lot of improvement on that. We'll just have to see how it goes. What are you going to notice from these changes? What do they mean to you? For us, the changes will make it easier to add new years. So like during the the years of 2014, 2015, where we had big droughts. You know, we didn't have, you want to be able to capture events like that in your data set quickly. We had a lot of people wanting us to incorporate those drought years and then the flood year of 2017 in the ensembles and so forth. And so this will make us more nimble and able to do that. As we go each year, we'll be able to more quickly add new years to our set. The underlying calibration data, historically, the co-op data was not data that we used in our operations, and it had different error characteristics than the operational data set that we used. So we always had to make a translation as to what that means for our operational data set. And now the two will be a lot more like each other, and so there shouldn't be as much adjusting and adapting as we've had to do. It's not likely that you're going to notice any changes to our operations on your end, actually. Changes to the ensembles really shouldn't be noticeable. And as I said, there's this trade-off between advancing your science and keeping up with your new tools and infrastructure, and trying to keep working with a consistent set of historical data that you can know what the characteristics are. And so we're not really anxious to make those changes, but they need to be done. And we've been transitioning and thinking about this for a long time anyway. We finally have had the tools and the skill sets in our office to make this happen, so we did it. The nice thing about the GFS version 12 is it'll run 4 times a day, so it'll always be available for our operational runs. When we go to 24-hour operations, we kind of hacked that for this GFS version 10, where we could run it 4 times a day, but it was really just incorporating the short-term weather. The long-term weather from the model was only run once a day anyway, and so that was you just kind of tacked that on. But this will be more consistent and fully operational for 4 times a day use. Let's see. The other big, talking about some of our collaboration efforts that have been pretty large, the forecast-informed reservoir operations has been something that's taken up a lot of our time, but it's a very valuable thing. It's like a real valuable application of our ensemble forecast for water management decisions, even proactive, that conversation that was not easy to have in the past because historically the forecast skill wasn't there to really make water management decisions based on future weather. It's gotten a lot better, and we have, with HEFS, you have the tools that you can manage that risk, and we're demonstrating that it's viable in some areas, and I'll talk about that. We're the Center for Weather and Water Extremes in down at Scripps has been a big player in really helping to advance the science and forward things like FERO, dealing with atmospheric rivers, and so they're helping filling data gaps for us, identifying forecast issues to focus research efforts on, and we're also we're engaged in that process, and also occasionally we'll review their scientific publications. And so it's a nice partnership where research is really trying to find practical ways to improve forecasts, and to be able to work with them is great on that. It just takes a lot of time and patience to do that. We're working with the Climate Prediction Center of the Weather Service and the Environmental Systems and Research Lab, part of NOAA's research, NOAA's research labs in Boulder, and then with the Department of Water Resources, and Janine Jones is involved with some of this. We're trying to improve the subseasonal to seasonal hydrologic forecasts, and so we got a project we're targeting. We're really trying to impact initially weeks 3 and 4 on our. We think there's some skill there, some ways to leverage the skill, and so we're going to tackle that. Ideally, everybody wants accurate long lead forecasts, a year or 2 in advance, but that's harder to do than to just want it. So, we're at least working on this actively and really doing it within a framework that utilizes our operational tools. And so when we get it going, it should If we can demonstrate that it provides value, we'll make that available to people. So it's kind of exciting. But again, it's not going to be any earth-shattering advances there, but incremental improvements are what we have to strive for too. We're also working with the Office of Water Prediction and the National Water Center on our hydrologic ensemble forecast system. Let's see, we want to improve that performance during extreme events, and also to bring some flood inundation mapping capabilities. I think I'm kind of going long on my time. We've got several different FERO projects. One of the big ones, Lake Mendocino, the initial one. We've got a final viability assessment that's going to be published by the end of this year. That's going to really lay the framework for starting on a water control manual changes. And so that's moving forward. There's a project on Prado on the Santa Ana River watershed. FERO for that looks a lot different, little different goals. That one's advancing. And now the Yuba and Feather FERO project is going. And that sort of builds on the work that we've done with the Yuba Feather forecast coordinated operations program that the state set up. And so this is really looking at bringing the proactivity into that project of really seeing how we can use forecast information to manage the watershed. And then the Truckee Basin, there's one going, and also for the Klamath Basin. And so more work for us, but more opportunity to keep our stuff relevant. With that,